But then when the sympathetic system is activated in the medulla, it actually has an interneuron that continues to try to deactivate the parasympathetic, and vice versa. So not only are we directly stimulating those nervous systems to go up and down, but those nervous systems are interrelated with each other to activate or deactivate one or the other within the central nervous system. That's also happening on the target cells themselves. Meaning, when you have a cell, remember in A&P, I hate this, but there's no other way to do it. Remember in A&P, you learn things as a singular cell? Like you learned probably that the beta 1 stimulation of the heart was one beta 1 receptor on the heart that causes that cell to increase its speed. But that's not the case. There's hundreds of them on that cell. And that's not the whole story either, because then you learned over here that there's a heart cell that has a muscarinic receptor that causes it to go down. But there wasn't really a time, I suspect, depending on the A&P instructor you had, that actually married those two things and say one single cell has both lots and lots of beta receptors and lots and lots of muscarinic receptors. Does that make sense? And so what you have is you have a cell that has a parasympathetic neuron and a sympathetic neuron activating that same cell. So to further the finite control over what that cell is going to do, there's actually projections from the axon here that project over. It's called axon-axonal, where the axon of one is affecting the axon of the other. So where this is stimulating these cells to do what it wants it to do, it is inhibiting that part of it so that it can't release its chemical at that point as well. Does that make sense? So not only are there interactions within the medulla, but there's interactions on the cell itself that will activate versus deactivate something. So the net result of this confusion, because we have both of these things happening simultaneously. Do you think that this change that the baroreceptors are having on the parasympathetic and sympathetic is somehow going to change the effect that the ICP is having on the medulla? The receptors that are leading to this pathway are not the same receptors that are leading to this pathway. So the medulla is getting both signals at the same time. Does that make sense? The net result is that some things from one system go through and some things from the other system go through. Right? What gets through? What do we know gets through? And you can continue now.
So the vasoconstriction continues
Because
the sympathetic nervous system signal is getting through to the medulla to cause that systemic, to stimulate the sympathetic nervous system to cause systemic vasoconstriction. And then the baroreceptor signal going up to the medulla is also getting through, causing the parasympathetic response of having the heart rate decrease.
Okay. So what ultimately happens here, right? So this is going to lead to that decrease in heart rate. Yes? Okay. So ultimately what we have is this is maintained. This is maintained. And something else is maintained. Two other things. One that's written on the board, and one that isn't, but you already know it. What else is maintained because one of the systems still controls that and the other system doesn't have anything to do with it? This is maintained, which means we're still pumping out more contractible blood flow because that's still sympathetic mediated and is not being controlled. Does that make sense?
It's not being controller counteracted by the
It's not, there's nothing to counteract it.
Yeah.
Because we're still sending that signal down there, and there aren't any parasympathetic, this doesn't happen on contractile cells. So the parasympathetic system isn't even present. So the net result is we still have an increase in contractility, and this causes one more thing that you already know, which is what? Conduction is definitely decreased, but this decrease in heart rate is going to cause something to occur too that's independent of these pathways. It's independent of this entire pathway situation.
Are you talking Frank Starling?
Yes, because what does Frank Starling say?
Well, when the heart rate drops, you're going to have more time for the heart to fill, which leads to a larger stretch, which increases contractility and more stroke volume.
Okay, so because Frank Starling is completely independent, Frank Starling, that law is completely independent of any signaling at all. It's physical. It's the alignment of the actin and myosin within the heart. More stretch lines them up better, which stimulates a higher contractibility. Added on top of that, that the sympathetic system is still increasing contractility. It tells you that because of Frank Starling and because of the sympathetics, contractility is going to be maintained very high. Contractility is going to be high, peripheral vascular resistance is going to be high, even though heart rate is dropping. Does that make sense? And stroke volume and peripheral vascular resistance, are both doing what?
Increasing the blood pressure.
Are going up. Heart rate is coming down. And the question then becomes, is heart rate going down enough to counter both of the other two variables that would increase mean arterial pressure? No. And the answer is no.
But the higher the blood pressure, the more the parasympathetic increases to decrease the heart rate, but with everything else, the sympathetic's still going up.
Correct.
So it's just going to keep
So we're still in a positive feedback loop, but now we're in two
positive
feedback loops, which is no better than having one. It's still going to end in their death when it's all said and done. Do you see what just happened?
Mm-hmm.
And how we got to a decrease in heart rate off that?
Mm-hmm.
So this increase in systolic, this widening of the pulse pressures, is related to increase in intracranial pressure. This decrease in heart rate is related to what? The barrel reflex. That's right.
The barrel reflex engaging the parasympathetic.
The barrel reflex. Yes, that is the barrel reflex. It's engaging those two systems. So that decrease in heart rate is barrel reflex mediated. This increase in blood pressure, mean arterial pressure, and systolic specifically, is ICP related, and now we have two of the triads that we see.
So, if you have a patient with, sorry, this is slightly off topic, but if you have a patient with Cushing's triad and they are conscious and talking to you,
They probably won't be, but okay.
Okay.
It's a late sign.
Well, that's helpful then. I was going to ask, how do you know when to call for a trauma activation? Would that kind of be like, because they need surgery, right, to like open up their brain and relieve the pressure?
They will need surgery right then. If you have a Cushing's triad unseen, survivability is going to be pretty low for the patient. Meaning this is by the time it leads to that triad, it's a late stage sign, right? Because prior to that, other little known facts, right? The sympathetic nervous system in the barrel reflex, forget this for just a minute. Now you can talk in general terms rather than specifics. What's the purpose of the barrel reflex? What is the purpose of the barrel reflex?
To not blow out the aorta.
Maintain blood pressure.
Regular.
To what?
Maintain stable blood pressure.
To maintain a stable blood pressure. It's homeostatic, okay? Consider it like this. You know your thermostat? Do you know how your thermostat in your house or apartment works? How does the thermostat work? If I set my thermostat at 75 degrees, how does it work?
So
He
it's
turns
like
on
3
until
degrees
it
if, like,
reaches
either
75
way.
and then turns off.
Okay, what's that?
It's like 2 or 3 degrees in either direction.
Okay, yes, if I set my thermostat at 75 degrees. That's my apartment's homeostasis. That's what I'm shooting for. It'll have a line above and below it. How sophisticated your heating and cooling system is will determine how controlled this line actually is. And what will happen is I can fluctuate in and out of that line and be fine. But if I drop below that line, the heat kicks on to bring me back up into that range. And if I go above that line, the cooling kicks on to drop me back down inside that range. So that 75 degree mark is where we're saying, this is our mark, and this is the range at which we are going to try to keep it within. But you don't want to keep it right at, you don't want 75 to be the locked number. Because that means your heating and air conditioning would be popping on and off every moment of every single day, right? You want to give it a range so that when you open your front door and cold air comes in and then you shut the front door, that cold air isn't going to pop your heat on because it's going to dissipate throughout your house. It might drop you a half a degree, but it's still within that range. So you're not going to waste energy popping it on and off. Does that make sense? Your body works the same way, relatively speaking. Your body works that same way. You have a mean arterial pressure that we are trying to defend. That's how we say it. We say we're trying to defend this pressure. You have this mean arterial pressure that your body's trying to defend at any given time. It is set with a range. That range is set on your baroreceptors. It's not the baroreceptors themselves. It's set in the medulla. It's set within the medulla to what the medulla is going to respond to. So the medulla has a set point that says, okay, if we get signals from the stretch receptors that are within this range, we're not going to do anything. We're not going to activate the sympathetic system. We're not going to deactivate the parasympathetic system because that's within an acceptable range of signaling that it's receiving. But if you go beyond that in one form or another, either we get more signals from the stretch receptors or less than that range that is acceptable to that range, then we will start signaling the sympathetic and parasympathetic systems to counter that. Does that make sense? Okay. One of the things that the sympathetic, let me back up. You're about ready to run a race. It's going to be a 3,000 because it can't just be a 40-yard dash, right? We're gonna run a 3,000 meter race. In order for you to run that race, what's going to happen to your heart rate and stroke volume in order to take care of the muscle activity that Annalise was doing a moment ago, because that was her cool running flail stuff.
It's a gift.
It's going to increase, right? But what's that going to do to the blood pressure?
Increase.
It's going to increase. What's that going to do to the stretch of those receptors?
It's going to engage them.
Which is going to do what to the sympathetic system?
Disengage the
And do what to the parasympathetic system?
increase the parasympathetic.
Which is going to do what to cardiac output? Decrease it. Well,
You don't want
decreasing your
decrease.
cardiac output in the context of something where you need an increase in cardiac output is not really helpful. Do you agree? So one of the things that the sympathetic system also does in the medulla is it resets the thermostat. Instead of defending a mean arterial pressure of, say, 75, we're going to defend a mean arterial pressure of, say, 90. So we've turned the thermostat up. So what that means is that baroreflex is not going to engage until later, right? Because that's going to let you run that race. Does that make sense? Okay, fantastic. That's happening here as well. So as the first stage of Cushing's reflex, before we see the triad happens, we are resetting that medulla to defend a higher pressure, which means it can accept a higher pressure. And as it's accepting a higher pressure, it takes longer before the baroreflex will actually, right here, before it'll actually start to take effect. Because we've reset the barrel reflex to defend a higher pressure already. So for a while, when we first start going into Cushing's reflex, we won't get that drop in heart rate because we're already defending a higher systemic pressure. Does that make sense? So it takes a little bit of time before that starts to kick in. By the time it starts to kick in, we have a massively high blood pressure already, right? Then when it does kick in, we still have mechanisms that continue to drive stroke volume and peripheral vascular resistance high. So even though we're dropping the heart rate, the drop in heart rate can't counter the effects that we have with the increase in stroke volume and increased peripheral vascular resistance. Does that make sense? Questions on that? So two separate things, increase in intracranial pressure and the barrel reflex, that are giving us two of the triad that we have. Good?
What specifically resets the map?
It's not resetting the map, it is resetting what the medulla oblongata is willing to accept. So as we start to activate the sympathetic nervous system,
Yeah.
part of what that does is conformational changes within the receptors on the medulla that will then be more or less responsive to signals coming in. So the receptors within the medulla are either more or less responsive depending on if we're defending a higher or lower blood pressure at any given time.
And the sympathetic nervous system?
In both the sympathetic and parasympathetic.
Okay.
In the neurons within the medulla that are engaged towards the sympathetic or towards the parasympathetic. We good so far? Everybody clear on this? Okay, so then why the third? Why the breathing changes?
Brainstem swelling. Or
Okay.
pressure.
Increased pressure on the medulla.
So
Physical
some
pressure.
of it is mechanical.
Mhm.
The irregularity of it is mechanical. That's true. There's also, as I was walking around, some of you, and when you look at it in books, you'll actually see it differently depending on the book, so you're all right. I saw some of you that had an arrow down next to respiratory rate, and some of you had an arrow up next to respiratory rate. So some of you were saying it was increasing, and some of you were saying it was decreasing.
It just goes up and
Doesn't it
down,
go-
whatever.
So it went up first and
And
then
some
it
of
went-
you named Shane Stokes. What's Shane Stokes?
Irregular. Fast, fast, slow, slow, fast, fast, slow, slow.
Good, so it's more than that. Give me more, besides just fast and
Volume
slow.
too, isn't it?
Shallow and deep.
So now marry all those things correctly.
Fast
and
fast
deep.
and deep, shallow.
Slow
and
and
deep.
shallow.
Fast and deep, slow and shallow. To something else. Fast, deep, slow, shallow, and apnea.
Yeah.
So the respiratory rate overall tends to drop because of those periods of apnea. But while they're breathing, they start hyperventilating. So it starts in this slow and shallow to fast and deep, back to apnea again. Why are we getting the fast and deep portions of Shane Stokes?
Blow off
Is it
CO2.
because of the chemoreceptors in the medulla oblongata that
Which are
are
measuring what?
carbon dioxide?
Because why?
Because there's less perfusion in the brain, so it's ischemic. Yeah, so it's becoming acidotic.
Yeah, that's exactly right. So because we have this hypoxic tissue, we have this ischemic tissue, but now we're talking about the hypoxia portion of it, right? Because it's hypoxic, we are in an anaerobic metabolism. We are producing more waste product and less use of oxygen. So we have a higher concentration of CO2, which by the way does what to cerebral blood vessels?
Constriction.
Dilates.
It tries to dilate them, but that's independent to everything, right? Because it's still not enough to take care of it. But we have that increase in carbon dioxide that increases the acidosis. That increase in acidosis starts to make them hyperventilate. But the pressure and the changes on the medulla and the confusion between sympathetic and parasympathetic system both being simultaneously activated in the medulla causes an irregularity to that breathing also. that leads us typically down either a Shane-Stokes or another irregular pattern to it. Does that make sense? And so then you have your triad. Good? What questions do you have on it? Yeah.
I don't remember what the most current thinking on it is, but I remember there being something about hyperventilating a patient that had head injury. What's the,
It's not.
okay,
You're gonna still find some controversy
Yeah.
on that. And I have a couple of articles that I'll send you guys.
okay.
There is some controversy that's still around that. There are some very, very specific times that they try to increase and decrease carbon dioxide just enough to make sure that you are getting the perfusion that you have there. But we used to do exactly that. We used to have these head injuries, and so we would increase our breathing, or we'd increase that hyperventilation to try to force changes in blood flow. But what we've found is that tends to increase the hypoxia that they're experiencing anyway. So it's not done except under some really controlled environments now. Yeah.
So the irregularity mechanically is because the medulla oblongata and the bones are being depressed.
You
like
have them being
physically
depressed,
being
that's gonna make some changes, yes. And the confusion that comes with one set of things trying to activate and deactivate the systems, and another set of things that's doing the opposite to that. And we have talked about the cardiac portions of this, but those two systems also deal with the respiratory center too. And so it's confusing to the respiratory system as well. So we get chemical changes in the medulla that are trying to change respirations. We have physical changes on the medulla that are trying to affect changes on the respiratory system. And we have autonomic nervous system confusion, and the result is an irregular breathing pattern that we get from it. That is sometimes mediated by the chemicals, hyperventilation, and sometimes mediated by the pressure, and sometimes mediated by the confusion of the autonomic nervous system. And you can see why it's complex. Yeah? So from this, we see a couple of different things. One, you get to see what ICP does. And two, the barrel reflex comes back to haunt you again. Didn't it just haunt you last week? Oh, great. So the autonomic nervous, I don't know how to express to you guys enough that I'm sure that at some point in time, someone probably told you that the autonomic nervous system is a really important system for you, like, be intimately involved with. From the fact that it affects our entire body, and half the drugs we give affect those systems in some fashion. But the barrel reflex comes back to haunt you in the context of this head injury stuff. And we have the ICP changes that are coming back to haunt you. Good? Yeah.
So for head injuries, some people some agencies give mannitol, right? And that's
Try to have a direct effect on ICP.
because it's just a diuretic, so they're just getting fluid out of
We're
the
just
body. in
trying to
general.
get rid of, we're trying to get rid of the fluid. We're trying to get rid of the fluid that puts the pressure on the CSF, that puts the pressure on the blood vessels.
And
But
that's
at the same time, if you were getting rid of systemic fluid, wouldn't it cause further?
There are some long-term issues with just doing that. We're trying to so realize that when we talk about managing a patient, there's a difference between this long-term management that's gonna get them to survive, and this short-term management that's going to get them to the moment that we can get the long-term management in place, right? Because these guys are gonna have to have their head drilled to try to get that pressure off and to really relieve that. But in the meantime, if they die because the ischemia is too great and it leads to
Hypoxia.
you can know because you want to use the word.
Infarction.
If it leads to a brain infarct of some sort, then we never get them to that point. So sometimes we'll use a drug to try to change the short-term acute effects of ICP to get them to the point where we can get them surgical intervention. Good? Questions so far? Get up and stretch, go to the bathroom,
What about Nelson?